Okay, so to try to get you an idea of where we're going with this whole conservation of energy thing, let's just work through an example. There's a cute little example in here. This is talking about mechanical energy, because I guess, yes, there's other, I guess, kinds of energy, but blah, 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 blah. Oh, FYI, a couple of whiles ago, I said something about energy like being lost to the universe, and your book does talk about that. It says it can't be turned into useful work later. So see, can't be turned into useful work later. So that just basically means that the work gets lost into the universe. So I felt good to know that the book agrees with me. Well, that I'm saying something that's valid. So the conservation of energy, what we can do is we can use it to solve problems like this, which is pretty cool. And again, this is all just still solving problems with F equals ma. We're just doing it from a different, perspective. We're just, I don't know. It's just the same. You can solve all these problems with F equals ma. We're just solving it with energy. Okay, so a particle is hung by a string, and the angle when it's released from rest is 30 degrees. What is its speed when it reaches the lowest point of its arc? Okay, so it starts here. So I'm going to define the ground as here. Okay. So I know, now am I ignoring, I guess I'm ignoring air resistance because it didn't mention anything. So that means my initial potential energy plus my initial kinetic energy has to equal my final potential energy plus final kinetic energy, and there's no non-conservative forces. Does that make sense? So there's no non-conservative forces. Initial PE plus KE equals final PE plus KE. Okay. So my initial potential energy is mgh, because I'm mgh from the top. Okay, mgh, so I'm a height of h. So my initial potential energy is mgh. My initial kinetic energy, however, is 0 because it just 0. I'm not moving. I'm released from rest. Okay. Now my final potential energy is, because it says, what is its speed when it reaches the lowest point? So if it's at lowest point, the potential energy is 0 because it's on the ground. You're like, well, it's touching the ground. It's just where I've defined the ground to be. The ground could be anywhere. And then the kinetic energy is 1/2 mv squared. And you're like, but what about the length of the rope? Yeah, it turns out that that doesn't specifically matter. It could matter for other questions that I might be asking later, like what is the acceleration, but we're not there yet. Okay, so the g's cancel out, the m's cancel out, and I end up with v squared equals 2gh, or v equals square root of 2gh. So that's the velocity. So, then I could also, if it asked me a question like, well, what's the acceleration of the ball at this position? I could be like, oh, well, the acceleration is v squared over r. Well, that's where that 1 meter might come into play. But really, this is just a real simple pendulum, a real simple way of kind of looking at these problems. But every time you put these together, it would be initial potential plus kinetic equals final potential plus kinetic. And depending on the system, there could be different kinds of potentials and kinetics and different things that have potentials and kinetics. And I don't know if we're actually going to get into that in this, but we'll find out, I guess. Oh, here's a little interesting question, kind of about the same thing. So a helicopter is hovering. When a panel breaks loose and plummets to the ground, the mass of the panel is blah. How much mechanical energy was dissipated by the air resistance during the descent? So that would be, let's see. We know that we have an initial potential and kinetic. Now there is a non-conservative force. I'm assuming because it's air, because it says dissipated by air resistance. So the work done by air resistance, and that's going to equal the final kinetic plus potential. Okay? So my initial potential energy is if it's at 1,000 meters, so it has a mass of 15. So this is always, well, not always, but right now, mgh. So it's 15 of a mass. It's 9.81, and it's 1,000 meters. And its kinetic energy, I guess whenever it falls, whenever it breaks loose. Oh, it's hovering. I was about to say, what is it? Is it moving? It's hovering. So I guess its initial velocity is 0. So remember, this is your 1/2 v squared, 1/2 mv squared. So since it's hovering, that's 0. Now this is the work done by air resistance. And then we need our final kinetic energy plus potential energy. I put those in a different order. Does that bother you? I can put them back in the same order. Final potential plus kinetic. All right, so the final potential energy is if I'm on the ground, there's no potential energy, and I hit the ground at 45 meters per second. So 1/2 mv squared. So I'm going to take this off to the side and do some math, maybe, if I'm lucky. Okay. So I've got math here. Awesome. Okay, so this isn't too bad. So 15 times 1,000 times 9.81, and then 45 squared times 15 divided by 2, and I'm going to subtract those from each other. Oh, thank you. That's an exact answer. It's totally what I wanted. This, oops, minus that is going to give me, okay, so I've got the work done by the air is negative 131,963. Negative 131,963 joules. So the work done by the air resistance, because the air was trying to keep it from moving and it sucked at its job. I have to keep saying that over and over out loud, otherwise I forget what I'm doing. So if it sounds like I'm talking down to you, I'm not talking down to you, I'm talking down to myself. So it does negative 131 kilojoules of work. Yeah, so it displaces, so I guess the mechanical energy dissipated by air resistance is 130, so I guess it's asking a slightly different, it's asking the positive, so it's putting an absolute value on it, is the total energy dissipated. But from a conceptual perspective, the air did negative 131 kilojoules of work, so we lost 131 kilojoules of energy into the universe by that panel falling to the ground. Like, we can't recapture that unless, we have powers to control all of the universe and energy. So it's a pretty interesting way of approaching that problem. I kind of like it. Yay!